So fresh.
Okay, so today we'll look into the first part of counting methods. We're looking into the arrangements and permutations. So arrangement is coming from if we need to solve problem. In how many different ways we can seat U4 in a row? So how many choices? How many choices we have for this place?
Oh, 4 times 3 times 2 times
We
1.
have four. For first place we have 4 choices. Then for second we have only 3 choices. Then we have only 2, and for last only
factorial.
1. That's equal 24.
It's 4 factorial.
And that we can be calculated using the notation factorial, where it's 4 factorial means 1 times 2 times 3 times 4. If we have 7 factorials, it will be 1 times 2 times 3 times 4 times 5 times 6 times 7 and so on. So that's factorials. In your CAS calculators, there is a button that calculates factorials. You just put how many you need to calculate and gives you number. So in arrangements, we counting in how many different ways objects can be arranged. And this is when there is no restrictions. Now, sometimes arrangements can be with the restrictions. Example, if we have, let's say, 4 boys and 2 girls, and we won't sit all of them in one row, so 4 boys, 2 girls, and if there is no restrictions in how many ways we can sit 6 students in a row.
I would advise
We
the
have
Boygel
6 students, it means 6 factorials. Because we'll have 6 for the first place, 5 for second, and that will be equal 720. Let me check. We have that 4 factorial 24, 120 times, yeah, correct, 720, yes. So we can sit 6 students in a row in 720 ways, if there is no restrictions. Now let's put some restrictions. If 2 girls must sit at the ends. So in how many ways they can be seated?
2 times
2.
1.
There will be 2. Now times in between 4 boys can be seated in 4 factorial ways. So that will be 48
True that.
ways.
How do you do that?
Because we have for the we can sit girl, but there are 2 of them, so we can sit here or we can swap them. And in between 4 boys, we already calculated that there are 24 ways that they can be seated. Makes sense?
Wait, so what was the restriction?
Restriction was in this case example that girls must sit at the end.
Like, it's 52 factorial, which is like a trillion.
No.
Can we do a deck of cards?
What?
Like a 52 factorial. For a deck of cards being reorganized.
52 factorials?
That'd have to be
Do it on your calculator.
My calculator's
That'd have to be a big deck.
No.
Should we show how that works? And should we all move 48 cards?
No. There is one way, one thing that not explained in your textbook, that missing in your textbook. In how many ways you can arrange object in a circle. So for example, in how many ways we can seat 6 people around the table. If we have 6 people, so we have in a row, we can sit them 6 people in 720 ways. In how many different ways we can put 6 people around the table? So arrange objects in a circle. And that will be, if we have n objects or n people, that will be n minus 1 factorial. So it will be 6 people into 5 factorials, which is 120. Why is that? Because if you have arrangement 1 person, 2, 3, 4, 5, 6, then we turn it around, move 1 here, 2 here, 3 here, and so on. It's the same arrangement. It's the same arrangement. So when object, this is not in your textbook, but you might have questions where you will need that. That if you arrange objects in a circle, n object, the number of arrangement is n minus 1 factorial. Make sense?
Yeah. So does that mean when you do a password on your phone and you guess it, you have a 1 in 3628800 chance of getting it right?
Depends how many characters are there.
4 characters of 10. Wait, I just stopped that up.
What are you talking about?
4 characters and there's 10 different numbers.
Now the next what we will be talking is exactly it's called permutations. And that's what we will be talking about. So let's consider in how many, if you're using 4 digits out of 10 digits, how many different passwords you can make. So for the first place, how many choices we have? 10. If the condition is that and digits cannot be repeated.
What?
The digits cannot be repeated.
So 10.
So we have for the first we have 10.
If it
For the
was-
second we have
9.
9,
8, 7.
8, 7. So we have
Well, 6, 5, 4, 3, 2.
you can calculate it.
720.
No, but you don't have it.
There's
because
70
there's
times
something after
72. 70 times 72 for 95,000. So on 90 times
It's 5,040, sorry.
56 will be, what you got?
5,040.
5,040, okay. 5,040 different passwords.
Yeah.
If you don't repeat any digit.
Yeah.
If you repeat, if you can repeat, you have 10 choices for the first, 10 in the second, 10 for the third, 10 for the fourth, equal 10 in the power of 4, which is 10,000 different combinations you can make.
Brett, I get first try every time.
No.
Yeah.
How we can, so what we're doing, we finding in how many different ways we can choose our objects.
Mr. V, did you hear Lucky's joke?
No.
He said, and he gets his password the first time every time.
So if you choose our objects out of n, when order is important. How would you choose R objects out of n object if order is important? The notation is we write P called permutation, and we write N R. Coming to this, that was typical permutation problem. We have it choosing 4 out of 10, and we got this. So that will be 10 factorials divided by 10 minus 4 factorials. 10 factorials divided by 6 factorials. If we consider, we don't need to calculate 10 factorials and 6 factorials. If we write what is 10, what is 6, with 1 times 2 times 3 times 4. 5 times 6 times 7 times 8 times 9 times 10, and this we have 1 times 2 times 3 times 4 times 5 times 6, and those cancels out, and what we have left, that's what we derived before. So for example, if you choosing if you choosing, say we have 6 people, and we need to choose committee, which will consist from the chairman and the secretary. Chairman and secretary. In how many different ways we can choose committee out of 6 people? We can choose committee, consists from chairman and
6 times 5?
we have that will be, yes, that's right, but that is permutation of we have 6, 4, we're choosing 2. 2 out of 6, and that is 6 factorial divided by 6 minus 2 factorials. So 6 factorials over 4 factorials. After cancelling out, it will let only 5 times 6 equal 30 different ways. Which in another way we can approach 6 choices for chairman, and when chairman was already chosen, we have only 5 choices for secretary. So we'll have 5 times 6, 30. So general formula for permutation, if for arrangement in a row, it's n factorial. In a circle, it's n minus 1 factorial. Permutations, choosing R objects out of n, when I underline, when order is important. Tomorrow we will look into the situation when order is not important, and it could have different name combinations. But permutations n r equal n factorials divided by n minus r factorials.
Wait, what do you mean in a circle?
People sit around the table, around the round table.
How is that different to a square table?
Different. No, it can be square
In a
table.
line.
Yeah, but in a round.
How is that
Compared to
different to an
different to the row, because when they so let's say 1, 2, 3, 4 people, and then we move them, make next combination, we make 1, 2, 3, 4. It's not any different. It's same, we have 1 sit next to 2, next to 3 to 4. If you will turn in them, that will be the same. In a row,
yeah, I understand.
in a row it will be different.
Yeah. Okay.
Okay, that's all theory for today.
Let's do it in practice.